So that makes it easy. We'll talk only about the diff. So I'm Ashok. I'm a product manager for a bunch of tools, which includes, so you have on the commercial side, we have the Arm DDT and MAP. That's managed by my manager, Patrick, who sits behind there, which is covering all the platforms, not just Arm. And everything on the left and the right, which is mostly the ARM-only tools, that's more or less my responsibility. So I'm going to give you a quick update on the GCC efforts that we're doing. The Open HPC is going to be covered maybe by Lenaro, but there's nothing much. It's just continues to make releases. One of the things we're trying to do, I'll cover as part of ARM compiler. The dragon there is LLVM, so that's one of the Keita compiler technologies we work on. Dynamo being something that might be interesting to this audience, considering it's more of an analysis toolchain, analysis framework. Based on these open source frameworks and downstream patches, which sometimes upstream doesn't accept, is ARM C++ compiler, the Fortran compiler, performance libraries, and instruction emulator. So that's broadly a group of 50+ engineers that are mostly based in UK, in roughly 2 different sites. That's our focus. So I just wanted to use this opportunity to explain why open source compilers are important. Now, ARM makes most of its money through IP. It's not software IP. Yeah, it's a hardware IP. So toolchain is very essential to get the most of that IP. And we picked 2 different toolchains to focus on. I think the reasons are obvious there. GCC happens to be the platform compiler for Linux. And GCC is what entire data center world kind of relies on. So GCC and all glibc toolchains and all the related items. And LLVM and Clang happens to be the framework that we rely on for our commercial compilers. Now, there are 2 commercial compilers, one for the embedded, the R, M, and A as it's used in the handheld or not server kind of scenarios. And the other one being, obviously, the server data center HPC. So the LLVM, Clang, and Flying projects, they form the basis of our commercial HPC offering, whereas the GNU is for us to enable Linux and data center. So that's broadly how we focus on these 2 toolchains. On the GNU A profile highlights, this is what broadly we did in the last 1 year. SVE is there in GCC 8. That was the first time it was added. It's reasonably well supported in 8. More changes are going into 9. You'll see when 9 comes out next year, more SV work has gone in. And then we have to do continuous architecture support. So ARM releases almost on an annual tick the dot extension. So we had to do 8.4. Later today, they'll announce 8.5. So adding those support becomes kind of the first task that the GNU team does. And plus, we look at continuously improving performance. So the performance usually is a combination of spec and what our end users report as important. So spec is used like a proxy, and it's also used by most CPU vendors to describe how great their chip is. To be honest, it has a wide variety of workloads, so we have seen that a lot of work we do in spec kind of improves other places as well. As an example, looking at spec floating point, we found that the POW log and exp and sign, these were required, and we had to write it from scratch because existing glibc was not great. And what happened as a result of that is some of our lab customers found that they also use it. WRF heavily relies on the exact same routines. And it just benefits. So even though spec is quite a maligned benchmark where people say, if you do spec, it's not real. If you do spec, usually it covers a lot of ground. So we focus on that. If you have any use cases where you see GCC not doing great, please let us know. The GCC team is always interested in solving some real user problems. So that's what I would recommend if you face an issue, whether it's G4 or GCC. ARM compiler, like I was saying, is based on a few projects. How does this work? Okay. So I'll just go through different parts of it. So on the back end, as a code gen, it's LLVM. So we share the optimizer and the code gen for both ARM v8 and SVE. On the front end, we have two different projects, one being Clang, which is primarily used for C, C++. Now, Clang is one of the very good C, C++ frontends because it supports your language features literally as soon as the standards is announced, whether it's C++ standards, C standards, or OpenMP. So we hardly have to do any work there. As long as we just integrate, it just works most of the times. On the PGI flang, now this is a new project that was, thanks to an NSA, PGI decided to open source their flang front end. They open sourced it May in 2017. It's been there for almost 1.5 years now. The good thing about PGI Flang project is now there are at least 3 major organizations using it. NVIDIA being obvious one, because PGI compiler is mostly based on Flang. We use Flang project as well for our commercial compiler, and a lot of issues that NVIDIA and PGI never encounter because it's not used in an x86 LAN shows up, and they're quite appreciative of it, and they keep fixing it. And recently, AMD provided an experimental compiler, as they call it, based on Flang. So there's 3 large organizations which are trying to see how Flang can become the great project like Clang is today for C, C++. Any questions on this? Okay. So what have we been doing in last 12 months? We've added some of the Fortran directives like IVDEP, force vectorization, disable vectorization, those kind of things where our vectorizations is not able to pick up right now. Debugging, thanks to our legacy from the Forge product, we know that PGI compiler is not one of the best when it comes to debugging, so we're fixing one by one more and more issues that crops up in debugging. Fortran 2008 and OpenMP 4.5, it's a combination. So PGI have been adding more features into Flang, supporting more of Fortran 2008, and we've also been adding some of the things that we encounter in applications. So most of the time, what features in compilers is driven by what our end users report and what applications are kind of interesting to our end users. So it's mostly the application-specific tuning and optimization which leads to what happens in the compilers. While we're doing this, a lot of work happens behind the scenes for SVE. The reason being there are chips which are publicly or privately announced, which is coming with SVE in, and ARM wants to ensure that LLVM has as good as support it can have for SVE. Performance libraries, standard slide. It's one of the closed source products that we have. It's maintained by a group of engineers in Manchester, led by Chris. So basically, we have been trying to provide as much functionality as an MKL provides, slowly one by one. Started with BLAS, ILEPAC. Last year, we added batch BLAS. And now we have added more and more FFTW equivalent functionality. So we've been tuning this mostly for ThunderX2 this year, plus an A72-based hardware which is available internally. And it's interesting that now we've been asked to do more sparse work. So HPCG and SPMB is something that we'll add for our upcoming release. But more we look into ThunderX2 and what it can do, or the current generation ARM hardware. Sparse might take more precedence or dense beyond HPL. So that looks like the plan. So you can see in what we've been doing in the FFT space. So some of those benchmarks like Gromax and Quantum Espresso may not make much of a sense for a ThunderX2 because it's more compute bound than memory bound. But what we are learning as a result of it is what is used in these benchmarks and these applications, and then it kind of helps us get ready for SVE when we are looking at how these libraries have to be implemented on SVE for different vector lengths. So more work is going on this. You'll see FFTW, more functionality being added. There's some things missing for Gromax to properly out of support right up now. That's going to be fixed. MPI, FFTW, API support is being looked at. Most likely it's going to be in. We'll have to see how much of it gets in our next release, but that's what's keeping us busy. On the open source libraries, there are some, I want to highlight the 3 libraries which are kind of related to our commercial tools, at the same time something that's Arm has been helping shape up. So optimized routines is a placeholder that we have where anything that's been developed from scratch from within Arm, we put it there. The reason is it can go to many open source projects. It can go to glibc, it can go to commercial toolchain, it can go to other places like OpenJDK and stuff like that. So it's implement once from scratch and then get it into some of the products. Now, interestingly, we've had, so there's a double-edged sword. So we open source it, at the same time we put it in our commercial because it makes it available early, because glibc takes forever. And a lot of our customers complain that, hey, this open source routine that you wrote and you put it in the public is giving more benefit than your closed source. They're actually the same thing. They can't give more benefit, but so sometimes maybe delaying open source may be a good thing, but there you go. So it's a double-edged sword. On the Sleep library, it's the vectorized math routines. We don't have a preference for a vectorized math routine. We are looking at libmvec as well. Sleep happens to be, again, conveniently licensed project. So we're trying to look at both of these. There are others which may be candidate for replacement of what you have in other platforms like SVML. So that's being looked at. Now, so far the problem was the Fortran compiler never actually did vectorization, so it never could support vectorized functions. With an upcoming release, that should be fixed. Now, what would that show up is, now we need to see on a TX2, whether when it has only 128-bit, how much of a benefit it gives, especially for doubles. Does it do 2x? Does it do less than 2x? Something we need to see. Perflib is something that's used by our Arm performance libraries team to find out what functions are called where, to understand basically BLAS, LAPAC. It's again open source, generates nice pretty graphs. Something I guess might be interesting if you're looking at finding out where Arm performance libraries or other open source products should do better. All this open source were combined into a combination, and it's called Arm Linear Studio, very creatively named. C++ compiler, Fortran comes from what you saw. It also has Forge and performance libraries. It's released last year at SC timeframe. We continue to make releases roughly every 2 months. Last one was 18.4. Next one is going to be 19 in a month. What does it have? Like I said, a whole bunch of libraries you already saw. It also includes the Forge and the performance reports. So you get everything in one place. You don't get the fully powerful version of Forge and performance reports, but you get enough to get started. So typically what we see is customers buying the low-end edition of Arm Linear Studio, where they get compilers and libraries, but going for full-fledged Forge and full-fledged performance reports. What's changed since last year Research Summit? I'll just cover the Forge performance reports part. There's much better support for Arm hardware now, whether it's Forge, which is DDT and map, and also performance reports. It's better interaction with Arm compiler and library. Like I said, we are adding more debugging features based on the DDT reports. And that's broadly what's keeping us busy, just making all these pieces working. Any questions on this so far? Right? The next part is I'll try and cover SVE, which might be more interesting. There's a lot of research potential and a lot of greenfield, brownfield, however you want to call it, the work. So I'll not bore you with what is SVE. I guess most of you would know what is SVE. What might be interesting to you is an update on the tool chain support. Okay, here we go. So on the Binutils and GCC 8, we already have, I think, as good as it can be to get started. So the full assembly support, full disassembly, and basic auto vectorization. LLVM 7 to be released anytime soon. It has full assembly and disassembly support. We have been working very hard with LLVM upstream community to add the SVE core auto vectorization support. It needs some fundamental changes to how LLVM represents its instructions and stuff, so it's taking much more time than we anticipated. For the emulation now, there is QEMU version 3, has support for emulations. If you want to run binaries, you can use that as well. It runs on x86 or native Linux. It's a user space emulation that's supported. System is not yet. On the LLVM and GDB and Linux kernel, there are mostly, I should update that. So at least the Linux kernel has full SVE support now. GDB also has full SVE support. LLVM ongoing. In terms of compiler support, which keeps kinds of interesting to different people, is in upstream GCC, you more or less have everything you need except for ACLE. ACLE is going to be just like ARM's intrinsic support for SVE. That's going to be added as part of GCC 9, slowly getting added one by one. GCC 9 expected April, May timeframe, but if you are willing to get your hands dirty with upstream source code, then you can get it as early as end of this year. More improvements are being added, partly for internal cores and whatever feedback we're getting from end customers. Upstream LLVM, we've got the disassembly assembly in. SV CodeGen ACLE, all most likely, fingers crossed. Next year when somebody talks about tools update, that'll all be upstream. That's the goal. So come LLVM 9, things will hopefully get in. The main challenge is what's called an IR that needs to change for SV support because it's vector agnostic. And that is causing a lot of back and forth discussions on upstream for patches to be accepted. What we are doing as part of just opening up our code, we will have a GitHub project either this week or maybe next week, worst case, which will have all our patches in public for people to see. And that will show what all we have done on top of basic assembly and disassembly. This will be shared with our partners. Some of them have showed more interest than others, so anybody can take a look at what we have, and hopefully we'll keep it updated every 3 months. On the commercial side, both are bare metal, embedded kind of tool chains and HPC tool chains. They both support, and we think it's advanced. Obviously, there's a lot more work to do. On the emulation side, like I said, you have QEMU, which supports full support. ARME is our Intel STE's equivalent, software development emulator. It's mostly for instrumentation, which is heavily being used for emulation as well in the past. Now, with QEMU being available, we are focusing ARME primarily for instrumentation, not so much emulation. And it runs natively on ARM. It's kind of two-way thing. If you have a decent ARM hardware, what it means is your SV code runs as fast. It's not slow like fast models. On the other hand, if you don't have a hardware, then I've seen people run QEMU and then on top of it run ARME, so on x86. So there's many layers of emulation there, but still works fast. So this is a nice slide, courtesy Miguel from research, who's I think presenting this exactly the same time in another conference. I just want to spend some time on this so that kind of get the idea of what the power of Dynamerio is and how we are using it and extending it. See, the blue here is supposed to represent ARM v8, which is like not having to be emulated. And it's still orange? Yeah. The orange is more the SVE side. So what we're doing here is you have a binary which is Arm V8 and SVE, and the Dynamo mostly takes care of the V8 bit. We have an ARME client which gets pulled in by Dynamo, takes care of the SVE part, and an SVE emulation API is being discussion with the upstream maintainer, where what it does is you can write a client which works on Arm V8 and SVE without having to change anything. There are some hooks we can check whether it's being emulated or not, which kind of frees us from having to support all kinds of emulation clients, custom clients, and also gives an opportunity to end users to just use Dynamo plus SVE as they want to. As an example, there were 2 clients that were implemented by the research and ARME team, SV, memtrace, and instruction count. They were part of available of 18.2. By the way, ARME is a free beta tool right now, and anybody can download it just by going to our developer. So what we do as part of this instruction count is basically, let me just go to the next one. There you go. So there's a simple loop example. What we do is you compile with HPC compiler. You can use GCC as well. There's nothing special about. So as long as any SV compiler, you can compile it, you get a binary, and then you run a Dynamo vector. What it does is it provides multiple information. So on one side, it gives you, for example, in this case, that, hey, look, there was 7 SV instructions were present, and 3 iterations ran, so totally 21 instructions. It kind of gives you an idea of how much of your code is being converted into SVE. It allows you to not profile the system binaries, which artificially shows too many instructions being executed. So it only says how many instructions from your application was part of this exercise, and you can figure out whether it's doing a good job or not. So that's my last slide. Hopefully you got a quick diff of what's been happening since ISC last research summit. Oh, sorry. And any questions?
Yeah, I think we have about 5 minutes for questions. So okay. John's going to walk around with a microphone, and since we're live streaming, wait till the microphone gets to you to ask your question. Just raise your hand. Got one in the back.
Oh, okay.
Yeah, hi. Andy Warner, HPE. Quick question, is any of the LLVM IR work you're doing also going to drive parallel IR?
So when you say parallel IR, vectorization, you mean?
Yeah.
Yeah. So it's mainly for that. And that's why there is right now a proposal from all other architectures where they want to do similar kind of vector agnostic. And there's a lot of discussion going on how do you fundamentally support in Caveum.
So you're looking at the forklift upgrade of the IR at the IR level?
To support any vector agnostic.
Excellent. So it's an industry-wide thing that
yes.
you're trying to run. So that means it's going to take longer, but it's going to be more persistent, right?
Yeah. So for example, if you look at the discussions, RISC-V guys are involved because that's another architecture which needs this. Or they still have not come with a specification, but they have similar concepts. So we are having a lot of discussion with them.
Okay, thank you.
Sure.
So any other questions? All right. So let's thank our speaker.
Thank you.
All right, so next up is Andre from University of Bristol. Let's see.
This is just left and right. Yeah?
It is. Okay. The microphone's there. It's live. So.
Good morning. My name is Andrei Poenaru. I'm a PhD student at the University of Bristol with the HPC group. And I'm here today to show you some of the early performance experiments that we've been doing with compiler tool chains on Isambard, the world's first production 64-bit ARM supercomputer. So some of you probably already know this, but Isambard is a new Tier 2 HPC service from the GW4 Alliance. This is 4 universities in the southwest of the UK. So we've got Bristol, Bath, Cardiff, and Exeter, together with the Met Office, Cray, and Arm, and funded by the EPSRC. It is a Tier 2 HPC center, which means it's sort of a regional level. It's smaller than Archer, which is national supercomputer, but a bit bigger than local systems that institutions may have. And it is named after the famous engineer Isambard Brunel. Got a picture of him there. A few key facts about the system specifications. It's going to be a Cray XC50 Scout. There's a picture of Simon standing next to an XC50. It's going to have just over 10,000 ARM V8 cores, and these are going to be Caveum Thunder X2, 32 core, 2.1 gigahertz, dual socket. It's going to have Cray's Aries high-speed interconnect, and obviously the Cray software stack, so compiler, perf tools, MPI, libraries. The system is actually split in 2 parts. We've got what we call phase 1, which was installed last year, and this has a few different platforms that are mainly there for technology comparison. So we've got some x86 nodes, some Xeon Phis, and some GPUs. And then the ARM part, the main part of the system, is phase 2, which is currently being brought up. And this we don't yet have full access to, but we have had access to an early part of the system, which is 8 of the same dual socket Thunder X2 nodes, which we've run the experiments that I'm going to show you today. So Isambard's core mission is to get researchers to run their applications on ARM and enable the sort of experiment that will hopefully show us how competitive an ARM-based HPC platform is in today's context. And our approach to this has been to take some of the most heavily used codes on Archer, the national supercomputer, and I've got some examples of their VASP, Gromax, Nandi, and so on, as well as applications that our partner institutions are interested in, for example, OpenFoam. And we've gone through a couple of stages of getting them to run on ARM, seeing how they do just out of the box, and then trying to optimize them to run as fast as possible and take advantage of the hardware that we've got. And we've actually run a couple of hackathon events where we brought together people from our institutions, the institutions in the project, and people that have actually worked on the applications. And we've generally found that the experience with running the stuff on ARM has been great. We've had very few issues. There was virtually no porting involved. Everything worked out of the box. In pretty much every case, it was just a matter of specifying the architecture flags. And actually, some of those are not even needed because they're implied. I just think it makes things more clear. And of course, if you use the Cray compiler, you just load the appropriate architecture module and you don't worry about the flags or anything like that. In many cases, actually, if you hadn't been told you were running on ARM, you may not even notice. You might just think this is a regular Xeon box. And now, following up from the hackathon at the university, we did a study into how the performance of these TX2 nodes compares to other current high-end HPC processors. And what I'm showing you here is a summary graph taking a few of the applications that I listed above, where you can see we've got 4 platforms. We've got the 32-core Thunder X2 SKU that is in Isambard, and then the top bin 22-core Broadwell, top bin 28-core Skylake, and a more common 20-core Skylake. And this is a normalized performance chart. So for each of the applications, 1 is the Broadwell performance, and then higher is better. These are all single node benchmarks because on the early access part of the Isambard system, we don't actually have the high-speed interconnect, so we thought it doesn't make much sense to run MPI benchmarks over Ethernet. But I think at a glance, it shows that the performance of the Thunder X2 systems is competitive with the Intel platforms. In some cases, it goes higher than Broadwell and even Skylake, for example, OpenFoam or SDLI. In other cases, it's a bit below, but overall, it's in the same general area. And now one thing we were looking at when we were doing these experiments is how the different compiler tool chains do on these applications and platforms. And what I'm showing you here is the compiler that produced the fastest running code for each of the benchmarks on each platform. And now some people may think, ARM is a new platform, the software ecosystem might be immature, you might have lots of trouble getting to actually compile and run your applications, there may be lots of issues. But if you look at what's happening on Intel, you don't have one compiler that does best at everything, and each of the compilers there has some applications on which it performs best. And then if you compare the results on the Intel columns with the ARM column, you can see that in a lot of cases it actually matches up. So for example, GCC is fastest on Gromax and CP2K on Intel, and it's the same on ARM. Then CCE does best for things like the and the same on ARM. So I think this is early evidence that the toolchains aren't actually that immature, and you can expect the same general level of quality on ARM that you can expect on Intel. But the compiler doesn't always tell the whole story. So what we've done is we've went into a bit more detail into the other components involved in building and running these benchmarks. For example, maths libraries. So what I'm going to show you for the rest of this talk is how these compiler toolchains all together compare on just the ThunderX2 platform. And I'm going to start with a selection of mini-apps. These are mini-apps that we've worked with a lot in our group at the university. We've run them on lots of platforms. We think we know them quite well. Arranged roughly in order of complexity, starting with the stream benchmark and then cloverleaf, t-leaf, and the harder snap and neutral. There's a relative performance graph as well, but this time we're looking at the 4 compilers on the ThunderX2 platform. We've got the latest version of the ARM compiler, the latest version of the Cray compiler, and GCC versions 7 and 8. And what we see is for the simpler applications, the 3 on the left, performance is quite similar, which is a good indication because it means they all do well. These applications don't use any libraries, and mostly it's a matter of vectorization. If your compiler can vectorize the code well, it will go fast. And I think this shows because in all cases but one, either the Cray or the ARM compiler is the best to use. Now, the odd one out is neutral, which doesn't actually vectorize because it's a Monte Carlo algorithm that's not really suited for vectorization, and we know it doesn't vectorize. So when you can't generate vector code, it looks like using the latest version of GCC is what gives you the best performance. And we think this comes down to just better instruction selection, which not only happens on ThunderX2, but also on Intel, by the way. And then an interesting observation here is when you switch from GCC 7 to the latest GCC 8, you actually lose a bit of performance in t-leaf for some reason. And now moving on to some of the mini-apps, some of the full application benchmarks that I introduced earlier. The first one is CP2K, which is a molecular dynamics application. It's quite a complex one to study from a performance point of view because it's not easy to find what the limiting factor is. There are some compute-bound parts, some memory bandwidth parts, and so on. For this, we're using the H2O64 benchmark, and this uses BLAS and FFTs. Our intention was to compare the ARM performance libraries on the BLAS side with OpenBLAS, which is an open source library, and on the FFT side with Cray FFTW library, which is part of the Cray software stack. But it looks like you can't use ARMPL for FFTs in CP2K yet because it relies on some FFTW specific functions that haven't been implemented yet. So what you see on the right is we're just using Cray FFTW, and we're comparing the performance of ARM performance libraries with OpenBLAS. GCC 7 and 8 do a similar job. This is a time graph, so lower is better. And then it looks like OpenBLAS has a very slight performance advantage. The ARM compiler doesn't build this. I think this is an issue with Flang. And if you try to build it with CCE, it will crash at runtime, which is the same result it will produce on Skylake, but curiously not on Broadwell. Next up is Gromax, another molecular dynamics application. For this, we're using a fairly standard ion channel benchmark using MD-run. This is a PME benchmark, and we're not doing any MPI. But actually, when you compile Gromax with MPI disabled, it will still use its internal threaded MPI implementation, they call it, so you still decompose over MPI so-called threads and OpenMP threads. And we found that you can do pretty much any combination here as long as you fill up all the threads in your system. So on the DX2, you've got up to 256 threads, and you can do 64 times 4 or 32 times 8 threads. The benchmark spends about 35% of its time in FFTs, and these are the results with just Cray FFTW because, again, we can't build with ARM performance libraries. Now, I should say here, this is if you don't change the code, which I wanted to do for this slide. I didn't want to use modified code. But the benchmark itself doesn't use any functions which are not implemented. It just, when you configure it, it checks for the FFTW Goro interface, which is not in ARM performance libraries. So if you comment that out, you will likely get similar performance to Cray FFTW. And you can see there the compilers. This is a performance graph. Higher is better. So it looks like GCC has a slight advantage here. And the Cray compiled binary crashes at runtime, which is the same thing that happens on x86. Next up is Nandi. We're using the latest version of Nandi. This uses the Charm++ threading library. It's our only Charm benchmark. There's no MPI. We're using the STMV test case, which again uses PME. It does use FFTs, but only a couple of % of the runtime is actually spent doing library calls. And this is the main reason why you don't see much of a difference between ARM performance libraries and FFTW on the right. We're back to time now, so lower is better. GCC 8 builds the code, but it hangs at runtime, and we think this is down to a Charm++ issue. And then CCE fails to build this both on ARM and on x86. And I've got there at the bottom a summary of the time spent in the FFT library, and you can see that ARMPL does quite a bit better than FFTW, but because this is such a small percentage of the overall runtime, it doesn't actually matter. So that's cumulative time over 256 threads, and you've got about 160, 260 seconds out of a total CPU time of 250 minutes. Next is OpenFoam. This is a fluid dynamics simulation application, quite a complex one, lots of C++ templating. It compiles everything down into small dynamic libraries, and it loads them at runtime as you need them, which has historically made it a nightmare for performance tools. We're using the RANS driver case with the simple foam solver. This is almost entirely memory bandwidth bound, so it makes it quite nice to analyze from a performance point of view because it follows the performance that you see on the stream benchmark. If you have a platform that has higher memory bandwidth, then it's likely that OpenFoam will go faster. It doesn't do any library calls, and it takes good advantage of simultaneous multi-threading. So if you use something like two-way SMT with the ARM compiler or four-way SMT with GCC, you can get up to 10% faster performance. And on the right, I'm showing the results with the different compilers, which again is similar between ARM and GCC. GCC 7, that is, because GCC 8 has stopped accepting the code. I think it's probably become a bit more strict, and it just says that some of the code that used to compile is no longer valid. And it also doesn't build with the CCE, which I think has been known for a while and is in the works. And this is not ARM specific, this is across all the platforms. Next, I've got the unified model, which is the Met Office's code. We're using version 10.8 here and a benchmark that we've taken from the Met Office. The caveat here is that it is quite hard to benchmark the on a single node. This is an atmospheric simulation application used for weather forecasting. So at typical scales, you're looking at tens to hundreds of nodes. And we found that when you run at such a scale, the performance profile is vastly different from a single node. It becomes a lot more memory bandwidth bound at scale. So I've included here a short section of the chart that I've shown towards the beginning of this presentation, which compares between platforms, because it shows that ThunderX2 is behind both Broadwell and Skylake, but we expect this to change when we go to a more realistic scale, because, as I said, we expect the code to become more memory bandwidth bound. And above that is the chart showing the result with the compilers. Of course, CC has always done very well at weather codes, and it wins here. The GCC and ARM, there's a small performance difference there, and you can't actually build it with GCC 8, but that's because of an internal compiler error, so hopefully this is just a temporary issue. And the final note about the when we were doing the inter-platform comparison test, we found that on Broadwell, the fastest version of the was produced using CC 8.5, which is an older version. So there may have been a regression going on, but because we can't use the same 8.5 version on either Skylake or on ThunderX2, this is the closest we can get. And finally, I've got VASP, where the picture is a bit different. We've only been able to compile this using GCC 7, so ARM, CC, and GCC 8 all produce some sort of errors. But what I can show you is compare the comparison between ARMPL and an alternative on both the BLAS and FFT side. And the graph you see there is a heat map showing performance. 100% is the fastest, and then that's the other ones are relative performance of that. And you can see that if you use ARMPL over OpenBLAS for BLAS, you get a slight performance advantage. And if you use Cray's FFTW over ARMPL for FFTs, you get a bigger performance advantage. Now, we don't really know why that is, and this is one of the things we're looking into right now. If you look at how the time is spent in library calls, both ARMPL and FFTW spend around the same total time. ARMPL does quite a bit better in the actual execution stage of the FFTs, but it spends more time in planning, and when you sum them up, it comes out as almost exactly the same number, but still FFTW is almost 20% faster. So we're not sure where that performance improvement is coming from. This is something we're looking at. And now I'm showing you a heat map that summarizes all the applications that we've gone through today. And the same as on the previous slide, for each row, 100% is the best performance, and then you get a relative percentage of that. This just looks at compilers, so it takes the best library combinations, if any, and just looks at how the compilers perform. And I think there's a bit of red on that chart. But if we look at what's happening, quite a bit of it is on the GCC 8 column, which we're attributing to either temporary issues that will hopefully be fixed, or the fact that it is no longer accepting code which is quite old at this point. And some of these build failures line up with the CCE ones, and CCE has always been quite strict. So perhaps that's an indication that some of the software code needs to be updated to keep up with compilers. And then we've got the few crashes that we've talked about. But what I want to highlight is that none of these issues is specific to the ARM platform. All of them we encounter on x86 just as well. The only slight exception is that one case, which does work on Broadwell, but it still doesn't work on Skylake. And then I've added two almost blank lines for OpenSBLI and Nemo, which are two other benchmarks we're working on, but we think we need a bit more time to get the results in order before we can show you. This is just to let you know we're looking at them. And now here's almost exactly the same thing as on the previous slide, but from a MATS library side. So they only look at library performance, and they take the best compiler in each case. And you can see VASP is in both. On the FFT side, that's where Cray FFTW wins. In Nandi, there's not much difference. And for BLAS, they're all quite similar. And now, before I finish, I wanted to tell you about this repository of benchmarking scripts that we've started. It's all available on GitHub. All of the results that I've shown you today are produced using scripts that we've published. These are really simple to use. You just do one command to build and run your benchmark. You select what application and platform you want. You tell it which compiler and library to use if you want to. If not, it will just use the best combination that we know of. And it will build a benchmark and run it and tell you what the result is in the same way that it was presented today. And we cover ThunderX2, Broadwell, and Skylake. Of course, on the systems we have used. So if you want to use this on your own system, you may have to do some slight changes. But these will only be minor things like paths, modules, and things like that. We want to keep those as easy to use and as portable as possible. And these scripts will show you all the specific configurations that we've used, all the flags, all the build stages, if you're interested. But also, the repository contains output files for all the benchmarks we've run. So if you want to look into more details about one of the applications that I've talked about, all the results are available there. You can just go through the whole output of the application. And we want to keep these updated as the hardware evolves. So as we move on to the main bit of Isambard and as software gets updated, we'll keep maintaining those. So I encourage you to have a look at them. And now, to conclude, I think we have seen that ARM HPC processors are in a competitive spot and can be a real alternative to common high-end CPUs. The software is in great shape. We've had very few problems. We didn't have to do any platform-specific porting or anything like that. And although we have had some issues when benchmarking, those were not specific to ARM. Those were the same issues that you would encounter on Intel. And finally, when we see you at SE, we are hoping to have the full Isambard XC50 system and with results to share. So with that, thank you. And here are some links to our paper and some of the tools I've mentioned. So if there are any questions? There's one there at the back.
There we go. There you go.
Okay, so you might have said this and I missed it, but are you running exactly the same MPI and threading combinations in all your tests? And can you just speak to kind of how you decide those? Because one imagines you might not end up with the same optimization points as you change the compilers.
Yes, you're right. So I've only mentioned it for a few of them where I thought it made sense. For pretty much all the applications, we try to fill up the system. So we've essentially tried if it's best to run without using any SMT or two-way or four-way, and we pick the best. And where we have had to do decomposition, so I think there's Nandi, for example, you decompose over MPI threads and OpenMP threads. We have tried a few different values, and we've picked the best to show you for this. If you go to the scripts that we've used, those will have all the parameters in there, and sometimes where we've made the choice, there are notes either in the comments in the script or there's a README attached to each application. And it will say, for example, when we run OpenFoam, we use 256 threads because we found this is better. Or when we run, I think, VASP, 64 threads was actually better, and this is why we're using it.
No more questions? Okay, good.
At the front.
The Keita Project, do you allow others to contribute to it as well?
We've not had any contributions so far. It's a pretty new thing. We're certainly not discouraging it. What we want, yes, we want people to have a look at them, and if anyone has any suggestions on how we can improve those, they are welcome. I'm not sure how these will work, and you can see that some of the scripts have been changing in format quite rapidly.
Yeah.
So if you just go and submit a pull request, I'm not sure what might happen because it may conflict with our plans, but if you come talk to us, we're definitely open about getting these in the best state possible. So the aim is to have a go-to set of benchmark scripts that you just run, and it gives you the benchmark value data at the end.
Okay. Now the question is, in the last time when you showed, you had other applications as well, like WRF, and so do you have plans to include them before SC, or?
Before SC, I don't think in the short term, there are definitely things we've been looking at. There were some applications we've had some issues running due to licensing and things like that. So we can't, we still have some issues with some of them. We can't run them ourselves. So it may take a bit more time before we integrate everything. But as I said, we plan to expand this as we go along.
Thanks.
Okay.
Anyone else? So
In that case,
I had a
thank you.
question for you, actually,
okay.
since we have time. You've covered a lot of different factors here, different CPUs, different compilers, different threading configurations, different MPIs. It's just the number of factors in the benchmarking study is really impressive.
Yes.
So do you have any general guidance for the people in the room who will be looking to do comparisons of their own codes? How can they do fair, actionable benchmarks based on something like you've done here? What would be your takeaway for them?
So this is a very interesting question because I think a lot of us here in the room who have done benchmarking have found that people do some benchmarks and then you go and do the same benchmarks and you find different results than they have found. Mm-hmm. And this is, again, one of the reasons why we have started this repository of scripts, because we want everything to be open and accessible. So if you are going to do your own benchmarks with some of these applications and not follow our methodology exactly, then I think it would at least help to see what we have done and why we have chosen, for example, some parameters, or why we're doing this particular test case for the benchmark, and try to understand what value it brings, and then decide if you're going to go a different route, or if you're observing different performance for a similar set of parameters, is probably time to question what we're missing. Does that answer your question?
Yeah, that's great. Thank you very much.
Thank you.
All right, everyone, let's just thank the speaker real quick. Yeah.
All right, so if you just give me a second, our next speaker will be remote, waking up extremely early in the morning. Dan Ernst from Cray will be speaking. Let's see, let me reset this. That's going to go there, and this has to go there. And don't worry, you'll not have to look at my picture for very much longer. All right, Dan, if you can hear me, you're ready.
All right, am I coming through?
All right, so one additional tidbit of information. When we do questions at the end, folks, you're going to ask the question through the microphone as it comes around. Then I am going to repeat the question through my earpiece. Unfortunately, we had some issues with feedback on the microphones. And then he will respond to the question once that's done. All right, Dan, take it away.
Okay. Hello, Cambridge.
It's really early in the morning there.
Okay. So my name is Dan Ernst. I'm a member of Cray's Advanced Technology team, and Jonathan graciously asked me to come give a talk about some of our work on advancing the ARM ecosystem for HPC over the last few years. I wish I could be there in person, but I had a conflict, so we're gonna give this remote talk a try. I'm going to start by talking a little bit about an observation we made. This is about a half a dozen years ago. And we went and looked, and we have a performance team at Cray that does a lot of evaluations of HPC applications. They have to do that for projection purposes, for a lot of RFP responses. They have to do that for acceptance purposes to make sure that our systems are running the way they should be in production. And so they spend a lot of time with applications. We collected that data and looked ahead and did projections against future architectures. This is a projection we did around 2012, and the 7 anonymized CPUs across the bottom were what we were looking forward to in terms of coming roadmaps. And the blue bars here are the memory bandwidth of those systems, and the red bars is labeled as Cray Marks, which is basically a marketing name for a collection of about 30 plus different HPC application benchmarks. So this is not things like streams or DGEM. This is things like, Gromax and MIL-C and MiniGhost and things like that, actual application bench. And what we saw here was a pretty startling correlation between bandwidth and overall, this is geomean performance. But you might say, well, other things in the architecture are changing as well as we move forward. It's not just memory bandwidth, it might be compute capability. And so if you also plot floating point operations on this chart, what you get is this. You get almost no correlation. The floating point performance was increasing rapidly because adding floating point units was really easy, but as we've all heard from the discussions of the memory wall over the past few years, adding memory bandwidth was getting a lot harder. And so we were faced not just with a sort of, well, we got too many flops, but if you think about it in terms of how the world was progressing versus what we needed, the industry roadmap trajectory was following a flops route. And what we knew for applications was that they were just tracking the memory bandwidth route. So the question came up of, is there a way that we can try and bend this the other direction, right? Try to make the industry roadmap look more like the bottom set, or moving those in real application performance as opposed to just moving peak floating point. The way we started approaching that was looking around at what other opportunities there were. And a big one we came upon was the initial pushes by ARM into 64-bit. ARM v8 had been released, and the number of companies are starting to look at producing chips that look like what we need. But a lot has to happen for something to get into the HPC market, right? We have to develop an entire ecosystem. Right, if we want to design something that's, build hardware that's supposed to address a certain market or a certain set of applications, there's a big list of things that you have to do, not just in hardware and all the pieces there, but in verification, in software side, and operating systems and compilers, and basically everything that you need to run software on your ISA has to get taken care of. In the ecosystem method that's promoted by ARM, a lot of this help gets taken care of, right? A lot of these pieces are covered by available open standards, as well as IPs available from a number of companies that really lower the overhead to entering into whatever market somebody wants to get into. And so we were asking ourselves, is this ecosystem, will this allow us to find more entrants in HPC, right, beyond the couple that we had been working with, right? Are there other ones out there? So we started looking at a lot of different places. We, I believe, in between 2012 and 13, surveyed and had meetings with something like 13 different companies that were doing ARM servers at the time. And where we ended up with was finding a company that was really sort of interested in looking at our market, and were willing to let's call it, move the bar, and try to address some of the things that our applications needed. That company, by the way, happened to be Caveum. Now, at the time, it actually wasn't Caveum. It's sort of a long story. But it was the team that was working on the Vulkan architecture, which eventually became Caveum's current Thunder X2 C99 series. This is a chip that really moves in a direction that we liked a lot. It added, on the bottom here, a lot of memory controllers, 8 memory controllers. And between that and having a reasonable floating point performance, it actually provides a lot of application performance, right? Directly to applications and not to superfluous benchmarks. So this was a company that we started working on this architecture, and this culminated last November, in us releasing our Cray XC50 with ARM supercomputer. And this is sort of the big piece. This box in the middle is text from the press release, and it says, world's first production-ready ARM-based supercomputer. One thing to remember is at Cray, we take the word production-ready really seriously, right? The computers that we built, the supercomputers we built, are put into places that have a lot of really important work that has to get done, and so we want to make sure that they're usable end-to-end, they're resilient, all that stuff. This announcement was also made with our lead customer, Professor Simon McIntosh Smith, and the Isambard project as part of the GW4 Alliance and the University of Bristol. And it also includes the Cray programming environment, which I'll talk about in a little bit. But I spoke a little bit earlier about the hardware ecosystem, and we looked at different processor vendors that were looking at bringing something into HPC, but I didn't speak too much about the software side of things. So there's a few pieces of software that needs to get addressed before we get to production ready. The first piece of that is a lot of the foundational work, the open source. And this is some data collected last year for an SC panel that the places that we're looking at, can I just get open source stuff, things that I need for my computing? The answer was almost completely, 98% of things worked pretty much out of the box. Everything was either supported by things like Red Hat or SUSE in their operating systems, or it was upstreamable, which means it was open source and you just built it on ARM and it worked just fine. So the open source really was there, but for Cray, production ready means a lot more than that. This is the programming environment for a standard Cray XC supercomputer. It's pretty all-encompassing. It covers a lot of things. Some of these things are Cray developed. Some of them are from the third party that are either packaged or things that we modify a third party. And some of it is just ISV software that we license. It covers everything from performance analysis tools that are mostly custom from Cray, along with libraries that are both custom and shared. A number of compilers and different programming models are all included. If we were going to claim that the XC50 ARM system was production ready, our feeling is that it should have covered pretty much this entire stack. All right, so what's in the XC50 programming environment stack? There it is. Now, in case you didn't notice, there was only one change, and that one change is that it turns out you can't get ICC for ARM. Instead, we'll be providing ARM's own compiler as well. So in our estimation of things, we feel that the Cray XC50 is a full production-ready system. We look forward to seeing what our customers can do with it as we provide it. So this has sort of been an update of how we are gotten to where we are now in terms of product. So it's, some early results from our end customer. Simon has come around and shown some of the performance that he's gotten out of the Thunder X2 parts that we're deploying in the XC50, and things have looked really good so far. We're seeing heavy speedups, and speedups that really reflect that original observation we made, which was that this correlation with application performance is really tied to bandwidth. But getting from that observation to application performance gains requires all the ecosystem pieces to be in place. And we're pretty confident that that's the case for current generation projects. But what about future generation products? So we've also spent a lot of time at Cray on how can we bring ARM not just to the present, but to where we think HPC is headed in the future. So in 2012, when we started looking at different options for trying to address application performance, we began not just browsing, but we spent and committed to a long-term R&D partnership with ARM, the Vulkan team, and in partnership with our customers. The first instantiation of this was the Department of Energy Fast Forward 2 program, which was a project to really accelerate the adoption of HPC technologies into the ARM ecosystem, joint between the three companies of Cray and ARM and the Vulkan team, which was at Broadcom at the time. We continue, by the way, this partnership. The Fast Forward 2 project ended in 2017. We are continuing some of this work in Path Forward along with Caveum and ARM as well. I've got some of the collaborators on the right that we've worked with over time at ARM Research and at Caveum. There are many others not named, including the guy holding the microphone. So what did we do in the Fast Forward 2 project? So the three of us have collaborated on a number of future HPC technologies. The first one is that Cray has contributed to, since about 2013, the development of the ARM Scalable Vector Extension, SVE. We've been sort of a silent partner up until last year, but we pioneered a lot of instruction set, vector instruction set features, and ARM was interested in our understanding of those features and how they could be adopted into modern architectures. In particular, we spent a lot of time with them on guidance of how compilers could address this instruction set, and so how the instruction set could be designed to be easily, or I should say, very friendly to compilers. We also spent a lot of time looking at different components of future HPC technologies that we wanted to make sure were in the ecosystem and available for use by implementation partners. So things this included were memory technologies and memory interfaces, new off-chip interfaces, software infrastructure, new software, management and things like that. But the focus here was on open standards. We wanted these things to be in the ecosystem for all to use, not just one proprietary set of vendors. And lastly, and I think most importantly, we partnered with the Department of Energy to try to understand the impact on end user applications of architectural choices. If we're trying to do application-driven architecture, it really requires that you understand the applications. And so we spent a lot of time looking at those and try to analyze those. And I'll give you some examples here in a little bit. Let's talk a little bit about SVE. This is a list of features of SVE that actually came from Nigel Stevens, the architect. And one thing to note about these features is a lot of them were pioneered on Cray systems once upon a time. And so it was in fact our pleasure to try to help ARM along as they were trying to implement these in a way that they had. They wanted to make it compiler friendly. They wanted to make it encoding friendly to their own architecture, and they wanted to make it performant. And so we spent a lot of time with them in a very data-driven way to look at applications, use cases, and usability by compilers of different features in the architecture. As part of Fast Forward 2, we actually prototyped SVE compilers because we wanted to evaluate how well could a compiler address this architecture. It turns out creating an entire compiler backend from scratch is a pretty large task. And so when we wanted to bootstrap quickly and start experimenting, we did an experiment, and we took our Cray X2 compiler, which is the version of CCE, the Cray compilation environment that addresses the last Cray vector architecture, the X2. And what we did is we transliterated the output. So we had it output into X2 assembly language, and then we had a script that went and basically took those instructions and changed them to SVE instructions. It's worth noting that there was a fairly close one-to-one match on a lot of cases. There's a lot of the similar structures as we just talked about, right? Things like full predication support and so on. This first pass compiler, which we called the WIC, the what if compiler, really allowed us to do some good experimentation with features to look at compilation. The other benefit of this is the Cray X2 compiler was extremely aggressive in terms of vectorizing. And so we got to see very clearly places where vectorization could happen in the end once you had a fully optimized backend. Some of the things this process could produce, obviously SVE vectors, but also predicated execution with a lot of different schemes. It was able to generate widths between 128 and 2048-bit vectors, all things that are capable from SVE. The benefit of using CCE for this was that it had full OpenMP4 capabilities, including the SIMD directives, which were useful in highlighting vectorizable places, especially in codes like Lulash, where there's a lot of out-of-loop vectorization. But it also had the benefit of some explicit memory hierarchy support, so we could do things like migration and do some experiments with that. This was followed on by a prototype of a native SVE compiler as we had the time to put into it. And you can see on the right, this is for Lulash, which is a hydrodynamics code, moving from CCE Neon all the way to the right, with the what if compiler in the middle and the CCE prototype on the right. We moved all the way from, there were vectorization, there were a lot of floating point operations and a lot of vectors in all cases, but the orange line here is what we call algorithmic flops per clock, which is basically how many flops per clock could we be running at if there was nothing but vector floating point, right? It's a measure of how dense your floating point code is, not just in terms of how much do you vectorize, but how well do you utilize the width of a vector. And so we've made steady progress, and so you can see that by the time we're into the SV prototype on the right, we've increased that by a good factor of 3+ over the baseline of Neon. Considering that we've only increased the vector width by a factor of 4, that's we consider that to be pretty good. All right, so to analyze applications, to understand their performance was a major goal. So if we're going to produce architectures well suited to HPC applications, we have to invest in understanding them. And we did that through investment in the modeling environment. So we developed an infrastructure in Fast Forward 2 that allowed us to analyze applications at the granularity that matters for HPC. A lot of simulators that you can find these days or emulators run at single thread. They do modeling and performance modeling at cycle accurate single thread or maybe a few threads, and they're at times excruciatingly slow. So what we developed was a modeling environment that we could run at full socket size, full node size, in a reasonable amount of time and still get pretty good results in terms of performance variability. Some things that are enabled in this environment include MPI and OpenMP all the way up to at least 256 threads, an instrumented emulation of SVE as it evolved because it was still changing as we were doing this work, for whatever vector width we'd like to simulate. We modeled the implementation details of SVE so we could look at different function unit properties like latencies. Also had a full memory model, including caches, DDR and HBM capabilities, the ability to do tiered configurations, and both online placement analysis of data as well as migration, both automated or software driven. We were able to evaluate a number of different prefetchers and other instruction set enhancements that would try to, outside of the vector unit as well. We had network on chip models, and also a trace format for the ability to interact with other simulators like those at our partners, at Arm and at Broadcom, they were also doing modeling at their own granularities and their own tools, and we were able to exchange trace files back and forth so we could share these capabilities with each other. We also did have some prototype runtime support for things like memory hierarchy management. Some of these things actually made it into our final product for other multi-level memory hierarchy processors. And the ability to have different thread maps to cores to control and pin threads. But the short version is this let us analyze full node size applications, not toy problems, full size problems, multi-gigabyte problems. And that was really important because some of what we were really focused on in Fast Forward 2 was data movement. And we were looking at this both from a technology standpoint, what hardware was available to try and help with data movement issues. So we looked at things like the HBM standard, and we wanted to make sure that was appropriate and for Arm ecosystem. But we also went in the application space and tried to understand what their memory behavior was beyond just bandwidth good, right? And we learned some good material. So, in more of the hardware side of things, we looked at power, right? The power required to deliver bandwidth at scale. It turns out that if you try to deliver the bandwidth required to really run an exascale system effectively, if you try to do that with DDR memory, you're already out of your power budget just in DIMMs. And so technologies like HBM, which are much more power efficient bandwidth, are crucial going forward. On the application side, we looked at things like, well, how well do these applications, could they deal with tiered memory? And there is a range of answers to that question. The graph on the bottom right is looking at different applications, mini applications that we looked at from the Department of Energy. Across the bottom, you have essentially the footprint of the application moving left to right. Right, the total number of pages that are accessed at various times during the program. And in the y-axis direction, you have the percentage of total accesses cumulative coming from left to right. And so, for example, the green bar at the top is excess benched. And you can see that about more than 90% of their accesses happen within the first roughly 20% of access pages. In our estimation, that makes excess bench something that in a two-level memory system could actually make use of multi-level memory pretty well, where you would put that first 20% into HBM or a similar technology, and then you could put the rest in a slower memory. But some of the others, as you can see, were not nearly as amicable, and many of them look almost like 60 or 70% of accesses are within the first 50%, and those numbers make it very, very tricky to enable two-level memory access in a performant way. So in the end, our experiences in Fast Forward 2 were really with the goal of enabling ecosystems, in particular the ARM ecosystem, with the HPC technologies that we will need and others will need to provide new HPC solutions as we move into sort of the next generation of computing. Right? The end of Moore's Law is really bringing a lot of diversification to silicon. And at Cray, we wanted to make sure that the technologies needed for HPC to thrive in this environment were in place and ready to be used. I do want to throw out one last ask. We are looking for collaborators, others interested in future Arm HPC technologies. Do you have applications you think we should be looking at that maybe we're missing? Do you work with bringing Arm HPC technologies like SVE into the open source world or open standards? I think we'd be interested to talk to you and see what ways we could help each other out. Thanks for your time. This is my contact information, and I want to express our appreciation for the support we've gotten through the U.S. Department of Energy and other sources in doing a lot of this work.
All right. So thanks for that, Dan. I think we've got about, let's see, 7 minutes of questions. So again, wait for John to come around with a microphone, and then I will relay them to Dan.
Hey, Jonathan, you cut out on me.
Oh, I know. I was detecting a feedback loop on my side, so I stopped.
Gotcha.
All right, so any questions in the audience? Going once, going twice. It's always the last guy before lunch that gets no questions. Okay, nobody's raising their hand. No? Okay. Well, I guess that's it. So we have a break for lunch, and everybody come back here, please, at 1400, and we will get started again. So the lunch, if you guys don't know it, it is back from the direction you guys came, under the registration area. And yeah, we'll see you guys in a bit. Thanks for coming. All right, Dan? No questions, okay?